Alright, welcome back to Mechanical Engineering 3250 Heat Transfer from Dunwoody College of Technology. And we'll be looking at the second skills, F2, on the fundamentals of convection. So this is coming on the F2A one. So if you attempted that today, I don't think anyone actually did. This is early February of 2021. This would be the actual solution to that problem. If you haven't attempted it, it's a good example of what that might look like when you get to this one. So without further ado, here's my screen, and we'll get started here. So what do we have? We have, let me switch over to a smaller pen. Seems to like to grab fairly fat pens. So characteristics of convection. We have a inner and outer surface temperatures, so we know what those are. And we know the interior and exterior air temperatures, and we know the heat convection rates, convection coefficients, and now we're asked to find the heat flux from the interior air to the wall, so that's 1 by that, from the wall to the exterior air, so that's 2, and from the wall to the interior air, that's 3. And then finally, is the wall steady state? That's the question. So without further ado there, I'm not trying to, there we go. So what does this mean? What are we going to do here? We might want to sketch this out. So I'm just going to put a little sketch over here. So I've got a inside temperature, TS1, that's 16 degrees C. T infinity I is 20 degrees C. HI is 5 watts per meter squared Kelvin. On the other side, something lower, we get TSO, or TS2, depending on what you want to call it, is 6 degrees C. T infinity O is 5 degrees C, and HO is 20 watts per meter squared Kelvin. So maybe the wind's blowing pretty hard or something that's quite a bit higher out here than it was inside. And so we'd see this coming along here. There's some temperature drop off there as we go through. So we're looking for, and we almost don't need to draw a thermal circuit. We could if we'd like, but one of the questions is whether or not we're under steady state. So that's one thing that we use when we are in steady state. That's a nice tool we have to analyze a system. So we're not going to do that yet. We'll do what they ask for one by one and see if our heat fluxes work out. And if they're the same, then they must be steady state, right? So what's coming in is what's going out, and we'll go from there. All right, so starting with number 1 here, right? We're going to look for, from the interior wall, T infinity I to TS I. So what do we have there? We get our heat flux is HI. Now this is from the wall, the air. So we're looking at T infinity I minus TSI. Alright, so we're going to fill in some values now. What do we get? So we're going to have 5 times 20 minus 16. So that works out to be 4 times 5 is 20 watts per meter squared. From the wall, from the air to the wall. Alright, pretty straightforward. So that's, if I had a negative, if I flipped these around, I would have found negative 20, and that would have still been, from the air, from the wall to the air, so kind of vice versa. Alright, so let's see, what's number 2? We're doing the outside now, right? The exterior air, from the wall to the exterior air. So this is TSO to T infinity O. I still get QX double prime is HO now. So I'm going to have TSO minus T infinity O. And what does that work out to be? Well, we get QX double prime is 20 watts per meter squared Kelvin times TSO is 6 degrees C minus 5 degrees C. Alright, so that works out to be 1. This is 20. QX double prime equals 20 watts per meter squared. And that's from wall to air on the outside. Oh, exterior. There we are. All right. So far, so good. It looks like we're steady state. We don't know what's happening inside the wall. We don't know anything about its conductivity. So presumably that's the same thing, that we're not generating something inside of this. That could possibly be a case, or maybe we had some storage initially. But usually if we had storage, we have the same heat flux going into or out of the same body. And then step 3 here was asking, is the from the wall to the interior air, right? So now we're doing Ts I to T infinity I. And this is the exact opposite of our first case up there. So we're going to have Qx double prime is Hi times Ts I minus T infinity I, which works out to be 5 watts per meter squared Kelvin, times 16 degrees C minus 20 degrees C equals negative 20 watts per meter squared. From wall to interior air. So I found a negative sign there. I had a positive in the previous state. In number 1, these are all 20 watts per meter squared. I'm going to say that's probably steady state. So there you have it. Nothing too crazy. Basic convection. How is this going to vary from our, I think it's F6? Well, we're told what our H values are here in when we get into chapter 7, 6, 7, 8, 9. We're going to be calculating what our H values are based on some fluid properties, velocities, other conditions. So that's the difference between the fundamentals or the characteristics here and what the the more applied or advanced convection will be like. So with that, we'll end here, and we'll see you in a few minutes on another video.